Okay, recording started. Thank you. Thanks for the reminder. Okay, so today for me, I'm going to make it very brief and short. Okay, because next week onwards, we still got time to cover. But this is an important topic, just as I mentioned earlier, right? I told you all on this topic 6. Okay, the main idea of this, if you can see my screen, I hope you can see my screen. Yeah, I think I can. I can see on my iPad. It's mirrored to my iPad. So I can see. Okay, so basically the key idea of this topic is to cover the ADC and DAC, the setup. So you can see this is a typical overall system of a typical system that you will see in any system. In fact, any of the measurement system that you have, okay, be it the lab or be it the industrial automation control system or something like that, or oil and gas or whatever, all will require this type of setup. Pretty similar. Of course, you may not need a computer, okay, because they may use embedded controller. Okay, so but you definitely at the front end you need some sensors. Okay, it could be a weapon systems that you got some gyroscope or whatever. Okay, this is still a sensor, right? So you need a sensor. This sensor usually has to be amplified, okay, or go through a signal conditioning circuit. Okay, go through a signal conditioning circuit. Then it passes through this thing called the analog to digital converter. All right. The idea of this analog to digital converter is to convert the analog signal into a digital signal. All right, where this digital signal can later on be, processed further. Maybe can store in the computer or such. Okay, so this is just a typical example that I'm sharing with you. Okay, so let's, okay. Now this one I think is okay. I won't cover this part. I want to dive straight into this thing called the, what do you call that? The code weave. Okay, now a typical system, wow, many people in and out of the room. Very, very busy. Okay, never mind. I'll try. Okay. Yeah, all right. So the important thing is that the ADC, right, the analog to digital converter is basically a chip. It's an electronic chip, okay, that will convert the analog quantity into the digital. Yeah. So we need to understand some of the terms. For example, what is code weave? Code weave is determined by the voltage range, because otherwise the ADC is just a digital chip, right? So it will require to take in the voltage, divide by the number of bits. Okay, 2 to the power n. N is the number of the digitizing bits. Okay, for the ADC. Okay, if you all come in, you all don't mind mute yourself, so that I don't have to mute you. Don't mind, because of the background noise and such. Okay, so yeah, don't mind. When you all come in, you all can mute yourself. Okay, thanks. Okay, so we move on. Now, I think I want to do an example with you today. Okay, now okay, this one, okay, this time round, this one maybe you all can just take note. This one, can you all, let me see, SAC should not be covered. SAC, yeah, this time round maybe not covered. Okay, I tell you what, I want to do one simple question, simple work example with you, so that you all get the gist of it. Okay, I cross out a few things, never mind, we'll come back to that. Now, because you see, over here, right, now, it is quite, how to say, it's difficult to just memorize this kind of formulas without giving you an example. You see, there are quite of this. You see, all the things are highlighted in this box here are important, right? You see, I want you to take note. You take note first. Then later, when I explain to you using an example, then you realize that, actually, I don't need to memorize this if you understand. Okay, but generally speaking, the one that I box up is important, but actually you don't need to memorize it in a way. Let me explain using an example, then you will understand clearer. Okay, so you will see some of these terms. called resolution. Okay, and then step size K. Okay, what it means for all these things. Okay, so yeah, not to worry, not to worry. Okay, let me explain to you, because whatever later I give you an example to explain, it actually covers all these things. Okay, let me give a very good example. Okay, let's take a look at this example. Okay, wait, let me see. I show you one. Maybe wait, let me see which is a good example. Okay. Let's see, let's start with okay, let me see. Let me give you a good example. Yeah, okay, this one. Okay, this is a good one because it is a word example. At the same time, you already have the solution in front of you, but I want to work it through with you, step by step. Okay, so maybe what you can do, you all can do one thing, because I need to use the whiteboard. Okay, I need to use the whiteboard. So what I suggest you to do, if you can, take your phone, take a picture of this. Okay, put to full screen. Wait, let me. Then you take a snapshot. Then you can make a reference to your image that you have captured here. Can you take a picture of this, ladies and gentlemen? Okay, take a picture. So I also take one here. I'm going to bring you to a whiteboard. I'm just going to explain one example. Okay, so not to worry. It's going to be a very brief introduction because I need to let you guys off at about 8:50. Okay. Okay, so if you take a picture, you'll take a picture. Take a picture of this one. Okay, can take picture. Okay, good, taken already. Okay, let's try to understand a bit now. Okay, I'm going to stop this screen share. If you've taken a picture already, okay, maybe I can send it to you guys. Also, might as well, since I already taken. Okay, let me send it to the group, just in case you haven't got chance to take, or maybe sometimes somebody come in late. Okay, let's send this to you guys. Okay, yeah. Okay, so I send it to our group, the lecture group. Okay, I'm going to stop this screen share. Then I'm going to use a whiteboard. Okay, so I'm going to share the whiteboard. Share this whiteboard. Okay. Okay, still recording my screen. Okay, I think if you follow along, okay, you will see that actually this topic is very easy if you understand the concept. Okay, now, okay, what we have right now in this type of ADC or DAC question, right? Because you must understand that we are converting, right? Okay, from either analog to digital. So basically, the key idea is that you're either doing a DAC, right? Can you see my whiteboard? I hope you can. Okay, DAC, right? DAC means what? You are converting digital to analog, right? Okay, can see, thank you. Digital to analog. Or you could be, let me see, okay. You could be doing ADC, doesn't matter. So you convert analog to digital. Okay, understand? So there's two conversion that you can take place, but actually one is one way to the other, or the other way, ADC to DAC or DAC to DAC is actually the same. The concept, the principle of the thing doing is the same. Now let me give you an example. Let's say I think everybody knows a binary system, right? Binary number system. I believe you are familiar. Binary, you're expected to know, by the way. This one you expected to know. And the other thing, you need to learn how to use your calculator. Okay, very important. Your calculator is your best friend in your exam, in the exam context. Okay, So why I say that now, if I ask you, right, can you take out your calculator? All of you, I can't see what you have on, whether you have a calculator there or not, but I think if you got a calculator, you take your calculator. Now, can I ask you, right, if let's say I got a number 64, I don't know whether you understand, I put this subscript here. What does this subscript means? This little subscript, I call it subscript. Subscript. Subscript means what? It's the base, right? It's the base of the number, right? Because we know base 10, right? You know what's base 10? Base 10 is the number system that we have been learning from young, right? We learn all the 1, 2, 3, 4, 5. Okay, this is called a number 64, but I put a base 10 here. So now if I ask you, right, basically it's basically 64, number 64. Okay, can you convert this into binary? Okay, how to do? Can you all convert for me? You all know how to do? I believe you know lah, this one. Okay, how to convert to binary form? Okay, what is 64? Of course, you take calculator. Now, in exam, we don't have time to use we are not going to do like, if you use a calculator, right? Calculator is the fastest way. Okay, so if I convert, if it's a 8-bit, let's say, okay, let me just type. This is probably very obvious. It's pretty obvious. 1 0 0 0 1 2 1 2 3 4 5 6 7 7-bit. 1 2 1 2 3 4 5 6 7. Is it correct? And I put base 2 here. You all know how I get this? Is it correct? Just to confirm, make sure everybody on the right page, same page. Okay, so if you put 8-bit, of course you put another extra 0. I can see Mr. Go put that. Okay, fair enough. You can put another extra 0, but it's not a problem. If it's your 8-bit, right? You put extra 0, no issue. Okay. Okay, if you say it's an 8-bit is correct. What you put 0 is fine. Okay, now what you do is that, okay, this one is a system, right? Of course, if I tell you, okay, 15, right? Base 10, we know it is, if it's 4-bit, is 1 1 1 1. Am I right? It's quite straightforward. Agree? This one. Now, how we get 15? Let's do the 15 one easier. So basically, each of these is a binary weight. I don't know whether you remember. Basically, how I get 15 is that this one is, there's a power, 2 to the power 0, right? 2 to the power 1, 2 to the power 2, and 2 to the power 3. So if I were to do the very long-winded way, so basically, anytime you see a 1, okay, very quickly. So basically what I do is that how I get 15, I take 1 because the binary weight is 1, right? So it's 1 times 2 to the power 3, am I right? Plus, okay, 1 times 2 to the power 2, right? Plus 1 times 2 to the power 1, right? Because of this power. Then finally plus 1 times 2 to the power 0. So naturally you will get 8 plus 4 plus 2 plus 1, right? So therefore you get 15. Okay, any question? This one is very simple. This is called binary weighted, right? So this is the weight. We call it the weight. The weights. This one. These are all the weights of the binary system because binary is base 2. Okay, this one is very, very simple. Very basic concept. But of course, this is just to introduce to you the concept, very basic. You're not expected to know because in the exam, we don't have time to do this. We just use straight the calculator. So therefore, make your calculator your friend. So some of you may be unfamiliar with your calculator, how to use the binary function to convert the binary to decimal and vice versa. So that one you need to go and familiar. I can't help you with that. That one you need to ask, maybe ask your friend or look at your calculator's instruction manual how to do that. Now to cut it short, right? Just now back to 64. Now I know that if you understand this concept, it's quite clear. This is the basic. This is very, very basic. In order to understand ADC, DAC, you need to understand the basic first, which is the conversion. Now, how do we come to this number here? Let's go back to this number 64. Okay, 64, right? So what do we do? So basically, each of these is a binary. Now, I think we know very well that if you see 0, you ignore, right? Because your 1 is here. If you replace the 1, let's say depending, if this is 0, I don't care really because it's 0 times 2 to the power of 0, right? The first part here. Okay, this portion. Anything times 0 is 0 already, so I can safely ignore. So I'm only interested in those with the binary 1. For example, here, right? It's a binary 1. Because why? 1, because it's going to be 1 times 2 to the power of something. The weight. This is called the weight. Okay, the binary weight. Okay, I hope you remember. Quite fundamental. Maybe some of you say, "Sir, why are you teaching this one so easy?" Okay, very basic. I understand. I just want to spend a few minutes just to make sure everybody's on the same page. Okay, so how do we get 64? So if I were to quickly count, this is 2 to the power 0, 2 to the, okay, you understand what I mean? This is 2 to the power 0. Oops, sorry, 2 to the power 0, right? Okay, you can see my screen. So this one is 2 to the power 1, right? 2 to the power 2, 2 to the power 3, 2 to the power 4, 2 to the power 5, 2 to the power 6. So if I were to understand this correctly, if you help me, it's actually 2 to the power 6. Just correct. Okay, you go and check yourself. 2 to the power 5, right? Okay, so that one is 2 to the power 6. So I know that this one is 6. Okay, so therefore, when I take this times this, I get 64. Do you agree? Everybody, I hope you understand. So this is what I'm trying to drive at. So the binary conversion part is very crucial in the ADC and DAC. Okay, you must know at your fingertips because later when we do the calculation, you straight away use your calculator, punch in and get the number. Okay, so if you understand this, I'm going to clear this whiteboard here. Okay, not to worry. I believe later at the end of the day, I believe okay, because I did the setting and this whiteboard that I've just written on, it will be saved as a PDF file. Okay, so whatever I've written here, it will be saved as a PDF file. You should be able to get a copy of this PDF along with the video recording, okay, of this lecture that I've touched on. Okay, so not to worry. Okay, if worst case you get the video you get the video with but I believe you will get the PDF later after the thing process. Okay, not to worry. So I'm going to clear my screen and go to the next part here. I'm going to go to the next I'm going to erase the whiteboard. Okay, anybody got any question on this first before I move on? Anyone? If you got question, you can type in the chat. If you're okay, then I will move on. Okay, nobody's at the waiting room. I hope. Let's see. Quick one. Okay. No. Okay. So not everybody's in. Okay. Let's move on. Hey, later on. Okay. Maybe before I later forget. Too engrossed already. Later on, right? Before 9 o'clock. You all have to go to MS Team. I'm very sorry. You have to switch to the MS Team. Later on we will all exit from Zoom. You all go to the MS Team, the lecture group, where Mr. Chan will wait for you all there at the MS Team. Okay, Microsoft Team, the lecture one. Sorry about the switching here and there, because the MS Team, I can't do the iPad thing like what I'm doing here. Today is the first time I'm using this, so I'm actually quite happy. So far, the way I see, I don't know about y'all, but I think y'all prefer something like this, right? I hope something that the lecturer can write on, right, and explain, right, rather than just showing you one PowerPoint slide after another PowerPoint slide, right? I believe. Any reaction? Anybody got anything? Y'all prefer something with a whiteboard like this? Is it?
Yeah, better.
Better, thank you. Thank you. Okay, very good for your feedback. If got feedback, please give us the feedback, and we try to always improve. Okay, so I managed to get during the term break, go and get one iPad, and then I go and pay on my own. Go and get the Apple Pencil, which is quite handy. So I hope it help you all. Okay, so school never pay money. School never pay me. So it's out of my own pocket. But it's okay. But I think for the good of the students learning, it's worth it. Okay, come, let's move on. So I'm going to clear this one. Okay, so coming back to here. Now, the reason why I'm going to explain this is that you need to understand one thing. Let's say, I need to draw a scale first to show you. Okay, let's say, for example, okay, if I were to draw a scale, okay, I call it a scale. You may call this analog. Let me explain this first. To be honest, if you understand this, this question is very easy. You need to understand one thing first. Now, if I were to draw for you two vertical scales like this, okay, if you allow me, sorry if my lines are not that perfect. We try my best. Okay, so let's say if I say that, hey, so I got this decimal 0 to 15. Okay, 0 to 15, right? Now, how can I represent this analog value that I've just drawn? This analog value can be anything. It can be voltage. Okay, it could be voltage. It could be current. For example. Okay, so this is the digital. Digital we know, right? Digital means the binary. Okay. Now the whole intention, remember, is to convert, let's say, analog to digital. So that why must be digital? Because the computer cannot understand. Computer only can read 0 and 1. Remember that. Okay. Okay. Computer only understand 0 and 1. Computer only understand this 0 1. Okay. Remember, that's why we need to convert so that we can store the data. Okay. Let's cut the thing short. Okay. So if I got the analog value, let's say we know that. So if I can draw steps like this, right? Okay, for example, I'm not going to draw to scale, but you can see what I mean. So let's say 14 and 15 and so on, right? 14, 13 and so on and so forth. So 1, 2 and so on. Okay. Now, how do I represent this in the digital space? Now I can draw using like a ruler drawing like that. I know that very well that if it's a 4-bit system, right? 4 bits. 4-bit means what? 4-bit means 4-bit means, of course, for example, like this, right? This is 4 bits, right? Okay, base 2 lah. 4 bits. Now 4 bits how many levels can you represent? If I may ask, do you all know? If I got 4 bit, I know that 4 I can, if this is my digital scale, the one in red is a digital scale. So if I got 0, 0, 0, I know that the maximum I can represent is what? You know what's the final end here? 16. Okay, very good. Some of you 16. Okay, good. You are giving me the decimal equivalent. But actually your 4-bit, if I were to write it in binary, the maximum will be 1, 1, 1, 1. Am I right? Yeah, correct. Yeah, I see some response there, Mr. Chen. Yeah, okay, yeah, you're right. 0 to 15. I'll explain shortly. Now 0, of course, I can keep doing this, but I'm not going to write all these things, because after a while you get quite tired of this, right? You know what I'm saying? Okay, I'm not going to write all these things, but of course, you know what I mean. I can write this binary pattern, the whole binary pattern. In strings of 1s and 0, right? This binary, I call it the binary pattern, if you like. Okay, so technically you can continue writing this binary pattern all the way until you see 1, 1, 1, right? That's the max, right? Maximum, right? The maximum thing you can represent. Now, my point is this. Now, if I have an analog equivalent, I can represent, it's like a mapping, if you see what I mean. You map on the right hand side to the left hand side. Now, how for a 4-bit system, right? Okay, now there's an expression or a simple formula that you probably already know. The maximum representation that you can represent is actually 15. Okay, 15. The maximum. You start from 0, remember. Okay, you start from 0, you will map it all the way to 15. How I get 15? Because it's what? 2n minus 1. Does this sound familiar to you? 2n. Oops, sorry. Oops, I accidentally clear the screen. But never mind, it's okay. No worry. It's okay, don't worry about that. Okay, never mind. Maybe it's good. I can clear the screen. So basically, what I'm trying to explain to you, the maximum, the F max, is actually 2n minus 1. It's okay. Don't worry about the screen. Don't worry. Okay, 2n minus 1, where n is the number of bits. N refers to, okay, refers to the number of bits. Hey, this is so important. I think you all should kind of pay attention. This one is quite very important. It's basic. Okay, yeah. Yeah, I noticed some of you you're starting to put in some in your chat. Yeah, okay. So if your n, if I tell you n is just now I show you the 4 bits case, right? For n is 4. We know that 2 to the power of 4 minus 1. Okay, 2 to the power of 4 is 16. 16 minus 1 is 15. That means that your maximum representation is 15. Which makes sense, right? So because why? You start from 0. Just now remember I show you, right? If this is your analog one, okay, because you start from decimal, I put decimal, I put a subscript here. I hope you all now get familiar. I put 10 here. I put a 10 here because it represents a decimal system. Decimal system, the number system that we are so familiar. Decimal system. Okay, that we are very comfortable with, right? Since we were young, we were already counting decimal numbers. So all the way until at 15. Do you understand? Okay, so there's a lot of steps in between. So you will run from 0, 1 all the way until 15. But in your binary equivalent, okay, your binary equivalent, okay, or your decimal digital equivalent is actually you're going to write in this form, right? 0, 0, 0 all the way until you see 1, 1, 1, 1. I hope you all understand this thing. Do you all see what I'm trying to do? I'm trying to do a mapping. So on this one is analog, the other one is digital. This one is a digital scale. This is digital. Okay. The one on the right hand side, the one in black, written in black is a digital scale. The one in the red color is an analog scale. So it's a one-to-one mapping. So if I may ask you, if any of you, if I say A, so or maybe one of you ask, so what is not the 13? Okay, if I ask you what is 13, so can you, if I were to dotted line across here, okay, what is this? What is the binary pattern? Do you know? What is this number here? Okay, do you understand what I mean? What is the binary? What is the binary pattern? Or yeah, 1, 1, 0. How you get this? Okay, some of you suggested this. Okay, how you get this? Now, there's simple ways to do it. Of course, it looks pretty trivial. It looks very simple. So, but why are you asking me? Like very simple. I just punch in calculator. Okay, fair enough. But I want to introduce to you this thing called the step size. Okay, if you allow me. Okay, I see your point. Okay, thank you for the response. Okay, you say 13 is 1101, right? Okay, fair enough. Sorry, this thing that I draw on this. What you see on the whiteboard that I just draw is not drawn to scale. I must confess first. This thing, okay, that is not drawn to scale. Please take note. I didn't not disclaimer first. Okay, not drawn to scale. Okay, so please have this in mind. It's not the point. It's not the intention to draw. It's not drawn. Okay, not drawn to scale. Okay, so 13 is this. All right. Okay. Now I want to introduce to you this thing called the step size. Step size K. Okay, I want you to take note. Okay, this is covered in the notes. In the notes. Okay, this thing called step size. Okay, let me erase this thing. This diagram here a bit cluttered already. Let me clear this whiteboard. Okay, let me clear this whiteboard and I redraw again. Okay, let's go back to the very basic again. Same diagram again. Okay, the analog one. This is so important. I would recommend you what I'm trying to explain, because this thing later on will become I will explain in a more, because the numbers will get very huge or very large. Okay, this is the you know what I mean. So I'm just using something simple to start off first to start the explanation. So this is 0 0. Sorry, this is 1 1 1 1. Sorry, this one is not 0. This is wrong. Sorry, my mistake here. So it should be 1 1 1 1. Okay, so here is 0 0 0 0. Okay. Now, just now I asked you a question, right? So, okay, I asked you 13. 13, right? Okay, what is the equivalent here? Okay, so some of you gave me a response. So you gave me this. Okay, fair enough. Okay, so how do I arrive at that? Okay, first of all, if I may tell you, there's this thing called the step size, K. Okay, K is, if you look at my notes, K is called the step size. Okay, step size, okay, equals to step size. Step size K, sometimes interchangeably we will use the word resolution. It's the same thing, same meaning. Step size equals to resolution. Okay, now if I tell you A, sir, you tell me, sir, this one if the step size is one volt, let's say, even let's say if I give you okay, I tell you that A, the step size of this is 1 volt, because your step size can vary. If this step size is 1 volt, how on earth I get this decimal number? I mean this digital value. How did I arrive at this? Okay, how? Okay, very simple. Now we know that if you're given a step size K, equals to 1 volt, right? Now how do I get this? How do I get this thing? If then my question was 13, right? How to represent it? Okay, so or vice versa, you can do it the other way also. Or if I give you the digital value, you can convert it into the analog value, provided I know what is the step size. Right? Okay, so what do we do? Yeah, so of course what you can do is you can calculate, because this is a very simple example. You can convert from one to the other, right? Okay, so obviously for this case, if I would take 13, right? 13 divided by 1 volt, right? And then I convert that number into a digital form. So therefore I get 1101. Okay, you understand what I mean? I'm just trying to get you the idea of thinking how to convert from one to the other. Okay, some of you, okay, maybe it might. All right. So, and vice versa. Now, this is a very simple example. If your step size is 1, it's very simple. All right. So, you take 13 over 1. You take 13 divided by the step size, because you know how many steps. Sorry. Oops, sorry. I accidentally clear this line. Oops, sorry. Okay. This way. Okay. Because each step, now the step size is a constant. Okay, so a step size, right? Step size, because your step size can vary. Example, in other questions, your K sometimes can be 10 millivolt or can be some other thing. Okay, but the step size for one step is fixed. So you know what I mean? So I give you an example. Let's say if you know that your one step is 1 volt, that means if I got I got 13 steps. Still got people coming in.
tak boleh kacau aku.
Yeah. Sorry, who is that? Maybe you can mute yourself. I don't mind. Thank you. Okay, I'm finishing soon. Finishing soon. But I think maybe the other example, maybe I'll save it for next week. Or maybe you all can look at just now the example I've given you. Then we discuss this thing next week. But the point here, the whole point here is that this number, the analog value, is called the full scale, FS. Maybe I will just introduce, maybe today's lesson really is just to introduce to you some of the terms. Okay, so you want to take note, FS, okay, FS, okay, in your notes, it stands for full scale. Okay, full scale. Full scale means the full scale output. Okay, it could be voltage. Okay, so the full scale in this case, in this simple example here, maybe let's give an example. This is volts. Okay, so the full scale here is 15 volts. Okay, full scale. So so if I want to know what is the K, okay, on the left hand side, K, right, is actually equals to the full scale divide by the total number of steps, right? Do you know how many steps are here in this 4-bit system? Total number of steps. Remember, what is the total number of steps? I call it the steps. Total number of digital steps, right? Or steps. How many steps are here? Can you tell me? Anybody? Do you know how many steps are here? From here to here, how many steps? How many steps are here? Do you know? Just now what did I mention? Yeah, 16. Correct. John, John, thanks for your comment. Yes, because it's 16. The total number of steps is actually 2 to the power of n, where n is your number of bits that you have. If you got 4 bits, right? 4 bits, 2 to the power of n is their total of 16 steps. In this case, there are 16 steps. Do you understand what I'm saying? 16 steps. But bear in mind that because you start from 0, all right, because remember, 0 to 15, total got how many steps? There are actually 16 steps. Do you agree? Because you need to factor in the 0. Do you understand what I'm saying? I hope you understand it. Yeah. Yeah, 16. Thank you, John. Yeah. So because you have 4 bits, 4 binary bits pattern system, you 2 to the power of 4 is 16. Okay. Yeah. 2 to the power of 4. 2 to the power of 4 is 16 steps. That means you got a total number of steps. There are 16 steps and they are equal in size. 16 steps, right? So if there are total of 16 steps, right? Now your analog equivalent also has 16 steps also. Same, right? Total. Okay. So the thing takeaway for tonight maybe okay, you first of all get yourself familiar with or get yourself comfortable with this concept. Okay, K is called the step size, right? Or the resolution it is equals to the full scale. Full scale is the analog quantity. In this case, let's say 15 volts. Divide by what? 2 what? N minus 1. Does it make sense? I hope. I hope you all may try to understand. Okay, so if you take a look at this example here, okay, your K, your step size K is actually 15 volt, right? Full scale, this is full scale, right? 15. Okay, divide by 2 to the power, just now I told you 4 minus 1, right? 2 to the power 4 minus 1. Actually, your K in this example is 15 divided by 15, which is 1 volt. Okay. Do you understand so far? You must try to get yourself accustomed to this new, maybe, I'm not sure whether it's a new way of thinking, but it helps. It helps a lot because I don't believe in you memorizing all these formulas. Yeah, this formula thing. If you understand the logic behind it, there's no, you don't even need to memorize. Yeah, I try not to memorize the formulas. Okay, it's very logical. You see what I mean? You take, if you see this whole idea, this whole question on this ADC, DAC is very logical and it's very simple and very logical. If you understand the concept behind it. Okay, we talk about resolution, we talk about the steps, okay, and so on. Oh, okay, I think maybe, okay, I think now is what, yeah, I think maybe we will stop here. Okay, we will stop here unless you got any question first. Okay, but okay, just summarize a quick summary what I've just talked about. Okay, I'm going to clear this screen first. One last summary slide. Okay, so summary, what I just mentioned. Okay, so and okay, some of the terms maybe some terminology, the terminology for this topic, terminology. Okay, some terms. So N refers to the number of bits, refers to number of the ADC or the DAC bits, bits in use. So for example, okay, your ADC maybe is 8-bit. Very common, 8 bits, 8 bits, 12 bits, or whatever bits. Okay, all right. N is the, okay, now K refers to the step size. Okay, step size. Okay, or sometimes in the notes, I refer to my notes, it's called resolution. So it is the smallest step that you can represent it. Okay, if you like. Okay, K step size. And full scale FS refers to full scale. Full scale means is the maximum. Okay, it refers to the maximum analog output. Maximum analog output. Okay, so in short, if you now refer to my notes, K, the step size, is actually equals to the Fs, the full scale, divided by 2n minus 1. Okay, maybe this is what I can summarize up to this point. We will stop here. Okay, so this is the thing. You see what I mean? I try to explain very simple things using 4 bits first. Then after that, next week we will progress to more bits, maybe 8 bits, and then other 12 bits or something like that. Okay, so this is the analog. Okay, this is the digital. Now, if you draw these two scale and place them side by side, I guarantee you any question of this thing you sure can solve. Okay, anything, because it is what I call like mapping. Okay, one map to the other correspondingly. You know what I mean? They it's like mapping. If you what I mean, it's called like mapping. Okay, mapping one map to the other. It's very simple. Okay, one is mapped to the other, or then you can do this thing called like a bit of like ratio if you want. Okay, to get the values. Okay, I think maybe we stop here. Okay, any question for me up to this point? I hope you all enjoy today's lesson in a way, because we started to use this. Sorry, I could have got the iPad, but because of the time, the circuit breaker and stuff, I could have got the iPad and my pencil earlier, but it's too bad because of the circuit breaker and stuff. Yeah, so I hope you all enjoy the lesson today with a new approach that I try to use using this whiteboard to explain things. Actually, this is my preference, my personal preference to explain to students. Yeah, rather than using I don't really like, I use a lot of PowerPoint, one slide after another. I guess students get very bored, and then you lose your attention also. So maybe in this way, it's a bit more illustrative. Yeah, worth the money. Yeah, definitely. I agree. Yeah, really, really worth it. The iPad with the pencil is really worth. Yeah, I hope so. Okay, so I think maybe all the best for your quiz later. I think I shall not hold you back anymore. Okay, I think other than that, if you got no question, you're welcome to leave the class and then join the MS team for Mr. Chan's quiz. Okay, so give yourself 10 minutes break. Yeah, sorry, yes.
The quiz, is it about ADC? Don't have, right?
No, not this topic, definitely. Mr. Chan told you, right? He said topic 3 or something like that, right?
Yeah, correct.
So you go and try all the best. Try
So the quest is after the MS team.
Yeah, at the MS thing, right? Mr. Chan will tell you what to do at the other side. Oh, sorry, sorry, I have to make your transit here and there. I'm very sorry. Sorry about that. Thanks, thanks for coming to my class. Yes.
Just to tell you that I send you the this result on this part B for the filter design.
Okay.
Take a look.
Can. I'll look at it.
Thank you.
Okay. Thanks. You all better go. Okay, we can take a quick 5 minutes break before you all go. Thank you very much for coming today. Okay, I appreciate it. Thanks. I will stop the screen share. Okay, and we will continue. I will send you all the recording, by the way. I will send you all the recording. Okay, thank you.
Sir, next week 6:30 is tutorial same, is it?
Yes. Next week will be tutorial. We got no more practical. We'll do tutorial.
Okay, thank you.
Thank you. Thank you very much. Okay, I will stop the screen share. Okay. Thank you. Okay, later I send them.